Hello, welcome back to Engineering Circuit Analysis. We're talking about three-phase circuits. The name of this section is Wye-Wye Circuit Problems, Wye-Wye Balanced Three-Phase Circuit Problems, Part 3. In fact, this is one of the most important sections of the entire class because I've really built, over the last 10 sections or so, or however many there are, a tremendous amount of background material, all culminating in essentially this problem, essentially. This is going to be our first real three-phase problem that will be very similar to how you will have something on your tests and your exams. It's a fairly simple problem, as you'll see, but this is really where it really starts. And in order to get here, we've had to do a lot. We've had to talk about what is a three-phase source, what is a three-phase load, what is a Y source, what is a Y load, what's a delta source, what's a delta load. And then I spent a lot of time deriving and explaining the difference between line voltages and phase voltages and how to convert between the two. And so up until now, you might have followed that stuff, but you really didn't understand, or you won't until this problem, why we spent so much time on it. Because I could have just jumped right into this problem. I'm serious, I could have. I could have drawn this and I said, hey, we're going to learn three-phase circuits, let's do it. And then you would have gotten to the end of it and been completely lost because you wouldn't know about all of those things that we studied. But now that you do know, at least kind of conceptually, we're going to put it all together. So this is what a typical three-phase problem will look like. Notice there's no circuit. To be honest with you, if these problems drew a circuit, most of the time they would be too simple and too trivial for you to solve. As you'll find out, all of the challenge in these problems is understanding the terminology and getting it right. Okay? If I drew the three-phase problem, then it'd be very simple. But I'm not going to do that. I'm instead going to try to confuse you with a bunch of words, which is what your exam will have. So let's walk through it and let's solve this problem. So we have a balanced Wye-Wye three-phase circuit has negative phase sequence. The line voltage at the source is VAB, is 240 times the square root of 3. This is all the magnitude at an angle of 90 degrees, volts, which is an RMS value of voltage. The line impedance is given as, here's a line impedance, and notice that it's in ohms per phase. We'll talk about that in a second. The load impedance is given as, again, something ohms per phase. Okay? The reason why they're given in terms of ohms per phase, and that's why I kind of explained that a little bit before, is this is a three-phase circuit. If everything's balanced, which is what it says right here, first you look and see, is the circuit balanced? It tells you that. If the circuit's balanced, then you know that all of the source impedances are the same, all the line impedances are the same, and all of the load impedances are the same. So instead of saying A phase, B phase, and C phase all have this impedance, what they typically say is the line impedance is this, ohms per phase. That means each of the three phases has the same value. Each of the three phases of the load has exactly the same value. So if I were going to draw the circuit in all of its glory, I would draw the A phase, the B phase, and the C phase, and I would put the values here for the load, which would be the same for each, and for the line, which would be the same for each of those. Now notice that because it says this circuit is balanced, you know immediately that you could draw a neutral conductor going from neutral to the left, neutral to the right. But since now you know if it's balanced, there's no current in that leg, you can just take it out. You don't need to draw that. So half the time you might see circuits drawn, if they're balanced, with a neutral conductor connecting left and right hand side, and sometimes you won't see it there at all. And now you know why, okay? So let's dissect this problem a little more. It's balanced, it's Wye-Wye, that's important, so we have Wye-Wye connections. It's three-phase, that's big duh, right? Has a negative phase sequence, that's critical. We'll talk about that a little bit later. Actually, for this particular problem, it's probably not going to matter too much, but for other problems it will be even more critical, okay? The line voltage at the source is given by this and so on. And here's the line and the load impedances. Okay, what do we need to do? Number one, draw a single-phase equivalent circuit. Okay, and single-phase equivalent circuit, as we've discussed in the past, is you simply just draw a circuit for the A phase going up through the source, through the source impedance, the line impedance, the load impedance, back, and then you go ahead and draw that neutral conductor from neutral left to right, even if in the real circuit it's not there, but from a single-phase point of view, you pretend it is and you draw it like that, and you don't bother drawing the B and the C phases. And that's a single-phase equivalent. Then we need to find the line current in the A phase, and then we need to find the line voltage at the load in the A phase. So it seems that everything in this problem is actually basically having to do with the A phase, because as I've mentioned more than once you solve for everything in the A phase, the B and the C phases are known. Since it's balanced, and you know the phase sequence, once I know the A phase current, for instance, I can find the B and C phase current because I know it's a negative phase sequence, so I know I can add or subtract 120 appropriately. We're going to have more problems where we end up doing that. But essentially, once you find the